Anyway, I will begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and this time we have just to meet together and study your creation. I just pray you'd guide our steps today, Lord. Help us to glorify you in what we do. And we pray also that we would enjoy the break that's soon to come. In your name we pray, Lord Jesus. Amen. All right, I have an example. Let me get this example out of my system and then I'll take your questions. Okay, guys? So I tried to change the order of the bounds example yesterday, and I didn't quite have it set up right. And if you look at my notes, I more or less have the same example, give or take an order of integration or two, on page 272. In fact, example 6.2.4 in my notes is, give or take, one of the ones I did last time. Here's how I should have set it up. I should have set it up. Well, let me kind of set it up this way. I have R is equal to, let's say it's the region x comma y, such that 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to x. All right? And then this is the one that's kind of fun to do. All right, so let me look at this again, two different ways. I'm going to forcefully do it the way it doesn't work to start with, okay? And so if I try to put the x bound first, so here's a picture of what we're the region we're integrating. You got the line y equals x, you got 1 here, 0 here. Happens that y is also in 1, right? So if I set it up for the x bounds first, my right x is equal to 1, my left x is actually equal to y, because this is y equals to x. So if I do my y bound second, I'd have integral from 0 to 1, integral from y to 1 of e to the x squared. I did my x first, dy. Right. So there, I'm setting it up in this sense, like it's x comma y, such that 0 less than or equal to y less than or equal to 1, and y less than or equal to x less than or equal to 1. Does it make sense that you could set it up either way? I mean, I haven't set it up the other way yet, but so here, the idea is you pick a point, right? And if you pick that point and you look at it, right, it has y is between 0 and 1, right? Okay? Y is between 0 and 1, and x is between y, which is on the left, and 1, which is on the right. So what's this kind of setup? We talked about it yesterday. We called this a type. This is the type 2 setup, right? Whereas what's given in my problem is the type 1 setup, right? So again, I'm purposefully doing this unhelpfully so that you can see why this would be a poor choice, right? You see why it's a poor choice? Because we can't do what? This right here, we can't do this integral, right? But if on the other hand, I instead write this as the integral from 0 to 1 and use this setup here, the type 1 setup, integral from 0 to x of e to the x squared. I did my y bounds first, I did my x bounds second. Well, then we're able to make progress, see, because, well, that's the integral from 0 to 1. And I've got y, the integral of this is y, e to the x squared, right? And I evaluate that from y equals to 0 to y equals to x. And that, whatever that works out to, I have to integrate. And it just so happens that with that order of integration, I get x e to the x squared dx, right? We should all be able to integrate that, right? That's a u equals x squared substitution. I don't really need to write it down. That kind of integration I just do in my head at this point. That's 1/2 e to the x squared. Now, of course, you can check me on that, right? How do you check an integration? It's pretty simple. differentiate, right? If I differentiate e to the x squared, I get what? 2x e to the x squared, but the 2 cancels the half and leaves me an x e to the x squared, which was my integrand before I integrated. That's a good sign. And then, finishing blow, 1/2 e minus 1. There you go. So the order of integration matters, right? And sometimes you need to switch the order in order to make the integral actually calculable. Any questions before I go on? The silver lining I should have emphasized yesterday is when we got the integral down to like we did one yesterday where I ended up with like integral of e to the x squared or e to the y squared from 0 to 1. Like there is merit in that because that at least meant that we could use a numerical method to finish the problem if we wanted to, right? So if you look at my example 6.24, I take that perspective. Anyway, any questions? No? All right, well, I will go on then if there are no questions. So here's one. Example 2. Suppose you're asked to integrate 0 to r, integrate 0 to the square root of r squared minus x squared, and then we'll go dy dx. How do we calculate this integral? So this is relatively easy. What do we do? We do the inside integral first, right? So what happens when you integrate dy? You just get y, right? So this inside integral just does what? Is it okay if I don't write down all the steps down this time? This one just integrates to the square root of r squared minus x squared dx. Oops. Umbilicus. One day. Huh. What is this? Mr. Penn. Mr. Penn Scientific Calculator. What is this? Have you... What is, you have a Mr. Penn something or other?
I have Mr. Penn, like, Bible.
Mr. Penn Bible stuff.
Does it have, like, a mustache on it?
It's got a mustache on it, yeah.
Yeah, I have that branded stuff. Yeah. They have,
it's like highlighters and stuff for your Bible.
Yeah.
So this is,
I do not know if they make
what is this? It's got a Liberty Math sticker on the back of it. Is this from the math department, like from some forgotten age or something? Did we have some sort of deal with the highlighter company to get calculators? What is this? This is not from a student. I don't know what this is from, but I have to look into this. This is interesting. I will talk to the forensics people. Okay, so now we got to integrate that. So how we do that? We let x equal to r sine theta. That makes dx equals to r cosine theta d theta. If x is equal to 0, that tells me that we've got 0 is equal to r sine theta. If x is equal to r, that tells me we've got r is equal to r sine theta. So what's theta? We change the bounds, right? So here theta equals to 0, here theta is equal to pi over 2. So I change the bounds from 0 to pi over 2. Square root of r squared minus x squared is equal to what? It's equal to r squared times 1 minus sine squared theta, also known as r squared cosine squared theta. So that gives me a square root of r squared cosine squared theta. My dx, remember, was r cos theta d theta. All right, so that gives me altogether r squared integral from 0 to pi over 2 of, well, apparently cosine squared theta d theta. And I think it's good for us to go through this because it may have been a minute since you've done this integral, right? But this is certainly an integral that I expect you to know and to not get stumped on. Like, you should just glide through this effortlessly. Okay, that's maybe a little bit too much. Maybe not effortlessly, but with some minimal effort, this should not stop you. Because you're like, I can integrate by parts. No! You cannot integrate by parts here. You use 1/2 the integral 0 to pi over 2 of 1/2 of 1 plus cosine 2 theta. Right? That's how we integrate this with trigonometry. And so integral of that is r squared, and then I've got myself a 1/2. That gives me a theta plus 1/2 sine 2 theta. There's a u substitution there, right? Of course, if you got this u substitution wrong, you might still get it right because at the end of the day, when you evaluate the bounds, that sine term goes away. So I get 1/2 times pi over 2 plus 1/2 sine pi minus 1/2 of 0 plus 1/2 sine of 2 times 0. Thank you. See, this is why you should want chalkboards. I cannot nearly approach this speed on a chalkboard. Chalkboards slow me down like 30% at least. I miss chalkboards. Where I went to grad school in physics, chalkboards lined the hallways. There are literally hundreds of chalkboards just in the hallways everywhere at Stony Brook. It's amazing. They got chalkboards outside. There are chalkboards outside of the building. Now, it's kind of dangerous to use those chalkboards because the story goes that like the mafia built the building, so like some of the brickwork on the outside is a little sketchy. So they do have like temporary awnings everywhere so the bricks don't fall on your head. But setting aside that, the chalkboards outside are really nice. I've never actually seen any bricks fall, but those temporary awnings were there the whole time I was there. Anyway, so this all simplifies to what? Pi r squared over 4. Because sine of 0 is 0, sine of pi is 0. These things you know, right? For those of you who missed a point on problem 4 of the quiz, it's because sine of something can be 0 if the input is a multiple of pi. So like x squared plus y squared equal to n pi would have given you critical numbers. There's an infinite family of critical rings for that function as it happens. Anyway, I will publish the solution, of course. Can you guys explain this problem to me? What have we done here? What is this integral representing? So here we're just integrating what? This is really, you could look at this as the double integral of dA, right, over the region S sub r. What is this? Well, it's not even that. It's not S sub r. Let's say it's whatever you want to call this. Pac-Man. There we go. I don't know. Can you draw me a picture of Pac-Man? What's Pac-Man look like? We've got what? 0 less than or equal to x less than or equal to r, right? That's the outside bound. The inside bound tells me 0 less than or equal to y less than or equal to the square root of x squared, r squared minus x squared. So what are we looking at here? What have we calculated? What's the region we're integrating over? Let me draw it for you. Or somebody want to say it while I'm finding my marker? A hemisphere. No, that's too much. This is two-dimensional. It's two-dimensional. Double integral. So we're going from x equals 0 out to x equals to r, right? It is a quarter circle. And so this makes a lot of sense, right? Did you say that? I mean, if you said it and I interpret it and I change what you said to hemisphere, then like, my apologies. I do this kind of thing sometimes, you know. But so this formula makes a lot of sense, right? Because a quarter of the area of a sphere, of a circle. Now you got me saying. Now I'm saying sphere. What's wrong with me? So the quarter of an area of a circle is what? 1/4 the area, right? Which is the area of a circle, pi r squared, right? This makes sense. So like, if I give this problem on a test and I don't leave you a lot of room for it, what do I want you to do? If there's like a 1/2 inch of space for the solution to this problem, what are you supposed to do? You're supposed to go, this is 1/4 of the area of a circle, but I know the area of a circle is pi r squared, and that would be the solution. Right? Yeah. But anyway, all right. On the other hand, if I say derive, you know, the area of a circle using calculus, then I actually want these steps. Yeah.
Wouldn't it be easy enough to do this just from calculus 1 methods?
Ah, that's a good question. What is the distinction between this and calculus 1 methods? What did we do for calculus 1? And is there a difference? So in calculus 1, we'd have been like, okay, so you got this quarter circle, right? And we're going to chop it up into what? Into these little, you know, little rectangles. We're going to calculate the area, the infinitesimal area of that little rectangle. And we're going to see that, in fact, that's the square root of r squared minus x squared dx, right? And we can draw such a, you know, such a little approximating rectangle for what? For 0 less than or equal to x less than or equal to r. Yeah? And then we add them up, which of course gets us to where? Like Calc 1 starts where? Basically right here, right? Calc 1 sets up this integral by adding up little approximating rectangles. So, yeah, I mean, technically, yes, you could also use Calc 1. And honestly, like that, I have a derivation in the notes of the stronger form of the Fubini theorem, and it's essentially just arguing that the arguments we made in calculus 1 still apply here. But if I'm also integrating a function, then we should be thinking about like the volume that's over this thing. You know, we would have like something coming out of the board, and we'd be calculating the dV for each little slice and adding up all the little changes in volume or something. I mean, that's... Anyway, any questions on that? Another thing we should define is the average. Do you guys know how to do you guys remember how we defined average in Calc 1, like of a function? So here's a reminder. F average over a closed interval a to b, it was equal to 1 over b minus a integral from a to b of f of x dx, right? That was the average. That was the average of a function over an interval, right? Well, now that we have functions of 2 variables, we can up the game a bit here. Now we can talk about f average over a region, and we can define that to be 1 over the area of the region times the double integral over the region of f of xy dA. So this is the average of a function, right? So let me, I don't know. All right, so if we can't do the integrals, then we're going to be at peace with it, okay? But we'll try this on for size here. What would be, like I'm not sure we're going to be able to do this integral. Let's try though. Let's calculate the average of x over the quarter sphere. Now you got me, I'm saying sphere again. Sam, this is your fault. Quarter circle. So what do I have to, I already calculated the area of the quarter circle, right? So yay, we got that done. So I just need to do what? I need to calculate the integral over the quarter circle of x dA. So that's the integral from 0 to r, integral from 0 to the square root of r squared minus x squared of x dy dx. I think this is going to go well. I think the integral is going to be easier this time. See what happens when I do the inside integral. I integrate dy, I get y, right? I evaluate y from 0 to this. It just ends up giving me x times the square root of r squared minus x squared dx. Does everyone follow me there? Again, we integrate dy, we get y times x, but y times x evaluated from 0 to the root just gives me x times the root because the lower bound contributes nothing. Nothing. Now, I can just make a u equals the inside of the square root substitution, right? So if I let u equal to r squared minus x squared, then like u of r is 0, u of 0 is apparently r squared. And so this integral, changing the bounds, I go for integral from r squared up to 0, and my du is minus 2x dx, which means x dx is minus 1/2 du. And so what I've got is minus 1/2 square root of u du, which I can change up for integral from 0 to r squared of, square root of u over 2 du. And what's that give me? What is square root? Square root integrates to 2/3, 2/3 times 3/2 power, right? What's that? Okay, so I got 1/2 times 2/3 u to the 3/2. I evaluate that from 0 to r, and that is going to give me 2's be canceling, so we get 1/3. That was an r squared. 1/3 r squared. Oh, what'd I do?
How did you switch it from r squared to 0 to r squared?
I got rid of the minus.
So when you
Flippity flop.
out switching.
Yeah, I mean, the integral, if I flip the bounds, I get a minus. Yeah. So then, laws of exponents gives me, this is just integral of apparently, is that right? R cubed over 3 apparently. Now that's not the average yet, right? What's the average of r? X average, if you like. 1 over the area. What's the area? We just worked it out. Pi r squared over 4, right? Times what? Times the integral of x over the area, which worked out to r cubed over 3. So what do we got? The average for x over the quarter circle is, looks like 4r over 3 pi. That's good. I would like for the units for x average to be a unit of length, If I had an x average which was like r squared, that would be dimensionally inconsistent and a little bit troubling. So I like that the answer has an r in it. That makes sense to me. And also, I think if you just kind of picture, what is 4 over 3, what's 4 over 3 pi equal to exactly? Can you give me a decimal? Will Mr. Penn do it? Oh, Mr. Penn is still alive. I wasn't sure. 4 divided by pi. Whoa, that was too much for Mr. Penn. 4 divided by pi equals, oh, can't do it. 4 divided by pi is too heavy a lift for Mr. Penn. I think maybe it's time for hospice care for Mr. Penn. I don't know. Somebody got a number for me? You guys are so... 0.425? 0.425 R-ish. So I think if you think about that makes sense, right? It's like somewhere in here. So if you look at the totality of the points that's in the quarter sphere, which I've drawn very badly, there's more close to the y-axis than there are away, right? If you think about like the x values. So it kind of makes sense it would be a little bit this way. And without any calculation, what's y-average? What's that? The same, right, yeah. Wait a minute. Yeah. Well, hey, I've got the exact answer. What am I? Oh, look at that. Man, this board is... See, they clean it with water, so if you just wipe it like that, that's where this junk comes from. It's because they haven't cleaned the board with board cleaner at night. Oh well. Let's see here. See if I can find you guys another example. Whoa. Oh, what am I doing? I just got done telling you guys the board cleaner won't work. What? Wait, what? Oh, phew. For a second there, I thought I didn't have the juice. I got to have the juice. All right. So, if you look at my notes, I don't know, maybe I've got, I don't know how many pages. I've got like oodles of examples of these, okay? Like there is no way I will ever cover them all in class. They're there for you to look at. And so there's many, many examples for you to chew on if you need examples. But I would recommend, after you understand an example or two in here, you just go try to do the homework, right? The recommended homework is useful here because there's lots of odd problems. You can try them, check the answers, right? Or, alternatively, you could start to one of the examples in my notes, try it, see, work it out, not look at the solution, and then see if you get my solution, right? Do my notes have errors in them? Yes, on occasion they do. If you feel like you found an error, email me. I try to fix them when I find them, you know, but anyway, here's another example. I am on example 4. And so here, I'm integrating from 0 to 1/16. I'm integrating from y to the 1/4 power to 1/2 cosine of 16 pi x to the power 5 dx dy. All right. So can we just do this integral? I don't know about you, but I personally do not know how to calculate the integral of cosine of x to the 5th. Now, power series, I know, power series. Fair enough, you could just convert it to power series and do it. But I've graded the quiz, and so that may not be the best course of action at the current implementation of power series. Let's see here. So y to the 1/4. So let's just take this apart. This means y to the 1/4 is less than or equal to x is less than or equal to 1/2. So the other thing we can do rather than power series is to change the order of the bounds. But to do that, we must understand graphically what's going on here. So this is the easy part that everybody gets stuck on, okay? Well, not everybody, but a lot of folks. So we have to understand, so that is directly from the bounds. Are we all agreed? Remember, inside out? This one, this goes with this guy, right? That's my x bounds. Now, I would focus my attention on this piece right here. What is this? This, if at the equality, we've got x is equal to y to the 1/4, right? Also known as x to the 4th equals to y. Okay, so that I know how to do. That's y equals x to the 4th. That's just this thing, right? So that's y equals x to the 4th, and then 1/2, I'll draw, well, x equals 1/2 is like here, right? Let's say. And so what's going on? This is my left x, this is my right x, right? And so I must be talking about, and this point right here is what? 1/2, comma what? 1/2 to the 4th power is 1/16. Okay, we have confirmation then. Geometrically, the area we're looking at is this thing right here, right? We're integrating that there region, yeah? So how would I set that up instead of as, so it's given to me as a type 2 region, right? This is a type 2 setup. How do I change it to type 1? Well, it is, yeah, we go back to Calc 1 basically, right? And we think about essentially taking an arbitrary point in the region, like this right here, right? And you just need to write down inequalities for it. First with x, let's say 0 less than or equal to x less than or equal to what? 1/2, right? So this is 0, that's 1/2. And how about the y? If I look at the y, if I make this little line like that, what can I see? I can see 0 is less than or equal to y is less than or equal to what? What's the top? The top one is y equals x to the 4th, right? So x to the 4th is my upper bound. This, what I just wrote in red, is a type 1 description of this integral. So, switching the order of the bounds, we have the following. Integral from 0 to 1/2, integral from 0 to x to the 4th, and then I've got cosine of 16 pi x to the power 5 dy now, dx. Notice that the order of the integration I switched around. That's actually very helpful here, because now the inside integral is just the integral of dy. What's the integral of dy? The integral of dy is just y, right? So I'll write it down. I'll write it out this time. I don't always write out this step, but I'll write it this time. So we've got y, cosine of 16 pi x to the 5th, evaluated from y equals to 0 all the way up to y equals x to the 4th, right? So the fundamental theorem of calculus part 2 is what I'm using here. And I take the difference. Of course, the lower bound gives me nothing, and the upper bound is everything. It's x to the 4th times the cosine of 16 pi x to the power 5 dx. Ah, now that's something we can integrate, right? If you don't know how to integrate that, you need to go back to Calculus 1. And I don't mean you actually need to go retake Calculus 1, but I mean you need to go back to Calculus 1, look up the section on U substitution, and go work 20 problems. I'm not joking. Do it. All right? Don't talk to your parents over break. Just do integration, you know. But don't tell your parents I said that. Anyway. Dr. Wang is very funny when he teaches Calculus 1, because he he gets really upset when the students don't fix their Calculus 1 skills in the middle of the course, and they just go on as if not understanding the product rule is going to be something that's a sustainable pattern for them. And yet they do. Anyway, Dr. Wang's hilarious. this is what we should make our u, right? If I make that u, that makes du what? 80 pi x to the fourth dx, right? So I have an x to the fourth dx here. So what this integral becomes is 1 over 80 pi sine of 16 pi x to the fifth. And I got to evaluate that from 0 to 1/2, right? Now, if you doubt me, differentiate it, right? Derivative of sine is cosine, and then I, by the chain rule, pull out a 5 times 16 pi x to the fourth, but that gives you an 80 pi x to the fourth, which cancels with this 80 pi, just leaving me x to the fourth. So that's the integral.
But you need to change your bounds.
I avoided that by just going straight to the antiderivative. But yeah, you could also change the bounds. I wanted to show both methods today, so I did. Now, here, if I plug in 1/2, what do I get? Well, this is kind of, oh, to the fifth power. Oh, thank you, such a relief. I was thinking to the fourth power. I thought I got sine of pi. I thought everything was going to vanish in front of me and just give me an integral of 0, but no. 1/2 to the fifth power is 1/32. 16 over 32 is pi over 2, and I think what you just said, Sam, was right. So I've got sine of pi over 2 after you work it out, right? And then the lower bound gives me sine of 0, which is nothing. So the answer is 1 over 80 pi. All right. Okay, so I could spend another 3 hours of class time doing every example in the notes, and it will not help you learn. I have shown you the method. You need to go do it now. So what we're going to do at this point is go on to triple integrals. So I'm going to show you at least one triple integral this week before break. This is my token example for you. And I'll go ahead and I'll lead with the example that's more or less like something I've put on many a test. And it's kind of a pain. But it's probably, now we have done some triple integrals already in here, right? But they were, what were they? They were integrals with constant bounds, right? All of the bounds were just numbers. There was no relation. But something that would be an interesting example of a triple integral, one which actually requires kind of like a type 1 or type 2 kind of thing. Although that's not what we say here. For a triple integral, you can think about it. So I'll just do this one. So here is x, here's y, here's z. This will just let be x plus y plus z equals to 1. All right. Let me disturb that slightly, just so it's more interesting. Let us make it 2x, like that. All right. If I do that, that's a more interesting plane. And what the region I want to integrate over in 3 dimensions is this sort of, it's not exactly a tetrahedron has 4, same sides, right? This isn't quite a tetrahedron because the faces, while there are 4 of them, they're not all the same, right? But it's kind of like a jilted tetrahedron. But this shape here, let's call that volume E. And what I'd like to calculate is the integral, which is a triple integral over E, of, let's do something relatively simple like z dv. Okay? So how do you set up a triple integral like this? So what you have to do is you have to come to an understanding of a set of inequalities which describes how you cut down 3 dimensions to that volume. So it's helpful for me to have the equations of some different things on here. Like, especially these vertices. What are these vertices? Like, what's this point right here? This point would be what?
0, 1, 0.
0, 1, 0. Very good. This point up at the top? Just like you did, 0, 0, 1, right? The x one's a little funky. The x one's what? It's the 1/2, 0, 0. Very good. All right. And let's see here. What else is going to be really helpful is to kind of look at this thing from a top-down perspective. So like here's y and here's x if you want me to like do that. So this line right here, which I'll make red, right, would look like this. My bad. It would look more like that, right? This point is literally that point 1/2, 0, 0. This point is 0, 1, 0. This is all in the what? This is all the z equals to 0. I'm drawing the z equals to 0, the xy plane here just on its lonesome. Notice that the whole shape is above this triangle, right? So I can definitely say this much. What's the equation for this line right here? It's 2x plus y plus 0 equals to 1. I get that from the defining plane equation. So if I solve that for y, I've got y is equal to 1 minus 2x. So check it out. If I pick a particular point in here, right? And here I'm just looking at the shadow of the point. I really want to pick a point in 3 dimensions, all right? I want to pick a point in the interior of there, like a point x, y, z, and I want to give you, for an element of E, right? An arbitrary element of E, I need to give you inequalities which describe that point carefully. So you can think of like all of 3 dimensions as like a giant piece of cheese. Okay. An infinite 3-dimensional piece of cheese. And what you want to do is hack off everything. Think of yourself as a sculptor of 3 dimensions. You're hacking off everything except for what you want. So to start with, you just do the most lazy one, which is, let's say, x. So I'd have 0 less than or equal to x less than or equal to what? Everything in x for this shape is happening between what? Between 0 and 1/2, right? So if I impose the inequality, 0 less than x less than 1/2, that gives me an infinite slab. It gives me an infinite slab, if you will. It's something like this. All right? This is infinite slab. It goes on and on. And then what? Then I can take that and I can chop it at this red line. But think about making that up and up and up, right? So I can do 0 less than or equal to y less than or equal to 1 minus 2x. At that point, I've shaved off another what? That basically is cutting this like this, right? It's cutting it. And you're left with what? You're left with this infinite triangular cylinder. Or feel like it's a triangle that's stacked on stack on stack on stack. And then finally, to get what we have, I have to get the inequality for z. What's the deal with z? What's the lowest z can be? Down here, right? So we have 0 less than or equal to z less than or equal to, what's the top here? Well, it's governed by the plane equation, right? So solve it for z. I get 1 minus 2x minus y. All right, so now we can set up the integral. And the way it goes, we have integral from 0 to 1/2. Short, air marker. Integral from 0 to 1/2. Integral from what? 0 to 1 minus 2x. integral from 0 to 1 minus 2x minus y. And then I've got my z, dz. Ooh, I regret doing z here. Dy, dx. At this point, you should know how to proceed, give or take. Let's do it, though. So I start by integrating z dz, which gives me what? I've got 1/2 z squared, right? So that gives me 1/2 1 minus 2x minus y, quantity squared, dy dx. That's my z integral. Now 1 minus 2x minus y quantity squared, it's probably useful to think of that as a u substitution. So I have an integral from 0 to 1/2 of what? If this is my u, if this is a u, for the y integral, I have u squared. U squared integrates to u cubed over 3. So I have 1/6, u cubed. Now, notice that there's a minus on the y, which puts a minus on this integral. And then evaluated from, well, that's the question. What is my bound here? What's u of 0? And that's u of y equals to 0, right? So u of y equals to 0 is 1 minus 2x. U of 1 minus 2x is what? Oh, it's 0, isn't it? So if I haven't done this wrong, that is the lower bound is 1 minus 2x, and the upper bound is 0, dx, which is equal to, integral of 1/6 1 minus 2x cubed dx 0 to 1/2. Now you might wonder what I did. What did I just do here? I traded the minus and the integrand for flipping the bounds. Yeah? And then, okay, so we can make a w equals to 1 minus 2x substitution. And if I do that, I've got like 1/24th w to the 4th evaluated from, let's see here, w of 0 is 1, w of 1/2 is, well, it's 0. So 1, what? Oh, what have I forgot? Like this integral, quality check here, should this answer be positive or negative? We're basically taking some sort of weighted average. We're integrating z over this region where z is what? It's positive. It better be a positive answer. What have I missed here? My w, so as you're doing this integral, there's a minus x here, right? So the antiderivative actually would be this. So the answer is 1/24th. Now here's a question. What's the average of z? What would the average of z over this tetrahedron-y kind of space be? What would I have to do? I'd have to calculate the volume of E and divide 1/24th by the volume. That would give me the average of Z. But anyway, I just wanted to do a token example. This is what we're about to get into. And then the other thing we're going to do after break is we're going to learn that other coordinate systems are very simplifying. Like the thing we did today with the cosine squared, we could eliminate that, obliterate it with a polar coordinate substitution. It would make the integral trivial. But anyway, all in good time. Thanks, guys.